Hello everyone. Today I want to talk about high-dimensional model explanations and the approach we took to develop them. This is joint work with Patel, who is now a PhD student at the University of Southern California, and with Zick, who is now at UMass Amherst. However, we did most of the work while we are all at the National University of Singapore. As you all know, machine learning models become more and more complex and become harder and harder to understand. And I assume you all know this because this hasn't been happening without the machine learning community noticing. Many methods have been proposed to explain machine learning models, a couple at this conference actually. There's however, a small problem. The problem is that a big chunk of the proposed methods focus on explaining the importance of individual features. We think that's an issue, and goal of this talk is A, to convince you that this is an issue, and B, to show you a method with which you can overcome this issue. So let's start with a small toy example. We have a black box classifier that tries to predict whether or not a movie review was positive. So you can see here on the left some reviews. The first is, this is not even a movie. The second is, this is a bad movie. And we assume that our black box classifier is actually pretty good at its job. So it's not just getting the prediction right, it's actually also getting the prediction right for the correct reason. And for these two reviews, a linear model explainer would almost certainly point to the fact that not has high negative influence in the first review and bad has high negative influence in the second review, and everything would be fine. However, if you look at the following review, this is not a bad movie, a linear classifier would already get into trouble because here not and bad interact, and it's unclear how a linear classifier would account for this fact. So, for example, a linear classifier could output high negative influence for not and for bad, but that doesn't make much sense given that the overall review is positive. So what we are saying is many of the existing methods can't capture the fact that not plus bad equals good, or in other words, they fail to capture synergies and interactions. And this is where our method comes in. Let's start with some preliminaries. We assume that we are given a model, and we call that model F. And the model gets as an input a vector x, and this vector is n-dimensional. And it just outputs a prediction in the set of real values R. More interesting, however, is the method to explain the model, and we call that I of f. And it also takes as an input the vector x, so the point of interest we're trying to explain, and it outputs the interaction among sets of features. So if you explain a set of features, you also need as an input a set of features. So now you not just can make explanations for singleton features, like linear explanation methods do, you can also make explanations for sets of features. The next thing we need is a value function that measures the intrinsic value of a set of features S. And here for this talk, we just assume that our value function takes in the set of features, the vector x and the baseline b, and the value of the set of features is just how much the underlying function would change if we switch the values of the features in the set S to the values of the baseline. In other words, we say that we switch the values in the set S off, the features in the set S off. I want to note that there's a long and interesting and ongoing discussion in the community on what is the right formulation of this value function S. Our method is agnostic to this. I just have given here an example, so to illustrate what a value function would look like. Otherwise, be absolutely agnostic to the exact implementations of this value function. Okay, let's zoom out for a moment and think about how to design a good interaction measure. And there are many approaches out there. As I said, there are many papers proposed already. The approach we took in our work is the axiomatic approach. That's an approach where you have a good mathematical foundation for your proposed method. So we say we define a set of desired properties, also called axioms, that any good interaction measure should satisfy, and then we demonstrate that our method uniquely satisfies these axioms. And the nice things about this is that we only need to convince you that the desired properties are good, and then math is doing the rest for us. However, our method can also be motivated via a second way, and that's the optimization-based approach. So we can derive our interaction measure as a solution of an intuitive geometrical optimization problem. And in a sense, the second approach is way more common. Many feature-based model explanations are actually local approximations of black box models. The most famous example would be Lime, but in a sense, methods based on the gradients are also just optimization-based methods. But for the main part of this talk, I'm going to focus on the axiomatic approach. So we need to talk about some axioms. The first axiom we defined is symmetry. And symmetry just says that features' interaction values are independent of the index and depend only on their intrinsic worth. So if you look at the classifier on the left and the classifier on the right here, the only difference is that the input order of the features is scrambled. And we say if that happens and the classifiers are otherwise identical, the explanation should also only be scrambled. The second axiom is generalized true efficiency. And this axiom is concerned with what should happen if somebody merges features together. And we say that an interaction measure should be immune to artificial merging. Let me discuss a little example here. Let's say we have the sentence, "This isn't an absolutely terrible movie." A glaring endorsement of the movie. And we have two parsers. The first parser splits isn't into isn't, whereas the second parser leaves these two tokens together. And what generalized true efficiency ensures is that if you know the influences of is and int in the left parser, you can calculate the influence of isn't in the second parser. So in a way, if you know the most fine-grained versions of your features, you can predict influences or interactions in the more coarse versions of your features. So people can't hide information or influence by merging features in some weird way. And the third axiom is also very intuitive. We call it monotonicity, and it's concerned with what should happen if you compare two different underlying prediction functions. Especially it's concerned what should happen if a set of features affects one function more than the other. It affects the other function. And we just say that the interaction in the first case should be higher. So if you're more important for one function than for the other, our interaction measure should reflect that. And to clearly define what it means, to be more influential, we define net contribution. And we define net contribution via the inclusion-exclusion principle known from set theory. And here's just a definition for a pair of features. So it basically means we take the value if we add both features to a set, subtract the values from the individual contributions, and finally add the value of the set, the initial set. And this defines the net contribution of a pair of features for a given set T. And of course, you can extend this to any arbitrary set of features S. And with this net contribution, you can define monotonicity as if for any set T in the set of features that are not in S, the net contribution of S to T is more under F than under G, then the interaction measure should reflect this. Again, if a set of features is more important, our interaction should be higher. The final condition is the limit condition, and the limit condition just says that the interaction value of the set of all features is equal to the added value to the prediction task. So we just defined the net value as slide before, and we just define if we look at the interaction of all features together, that should be precisely the net contribution. And the nice thing about this axiom is that it is the discrete derivative of the set function f with respect to the set n. So it links our approach to approaches based on the gradient. And with this, we can come to our main characterization results. And it states that the 4 axioms we just described are enough to characterize one very specific interaction measure, and that's called the Banzhaf interaction index, and is well known in cooperative game theory, even though this characterization result isn't known. And the Banzhaf interaction index is defined by this rather intimidating formula here. Let me break it down for you. So the left side just means that we uniformly sample a set, T, and the right-hand side means that we calculate the net contribution of the set S in the sample set T. Now let's look at some case studies to see if the problems we described so far actually happen in the real world. In the first case study we want to look at, similar to the toy example in the introduction, is the case study of movie reviews. So we looked at the IMD movie review dataset, and we took the BERT language model to predict whether or not a movie review is positive or negative. And one of the movie reviews out there is the following sentence: it isn't the greatest sci-fi flick I've ever seen, but it's not a bad movie. So it's exactly the type of sentence we had in the introductory example, where we have a negation of a negative word. And we can look what LIME, a very popular explanation method, a linear explanation method, would do to explain this. And LIME would assign positive influence to not and greatest, and some negative influence to bad. And you could start a discussion on whether or not this is actually a good explanation. And I actually don't want to start that discussion. What I want to show you is just how the Banzhaf interaction index would explain this prediction. Specifically, here we illustrate the Banzhaf interaction index for sets with one feature. This is the diagonal, so this is basically the linear influence. And for sets of size 2 with 2 features, which is the off-diagonal values. And the first thing you can note is that the linear version of the Banzhaf interaction index actually agrees with LIME, more or less. So greatest has positive influence, not has positive influence, and bad has negative influence. And it's something we observed over and over again, that in the linear case, most explanation methods most of the time agree. However, the interesting part is in the interaction among sets of size 2, because here we can clearly see that not and bad have a strong positive interaction, meaning we see that our language model picked up on the interaction, and our explanation method is able to illustrate that. And that makes a lot more sense than the linear version on the left side. In the paper, we have a couple of more of these examples to illustrate what can go wrong if you rely only on linear metrics. But now I want to focus a little bit on what can go wrong if you don't satisfy the axioms. So we could think, okay, if a linear method is bad, I just pick an arbitrary interaction method, and we say that's not a great idea. For this, we look at the UCI adult dataset. And specifically, we trained a small decision tree here, which has only 3 levels. And we look at the prediction of the following data point: a married woman with a master's degree and a capital gain of roughly $5,000 a year. And this woman would be predicted by our little decision tree as making more than $50,000 a year. That's the prediction task here. And if we look at the bands of interaction index, again, these sets of size 1 and size 2, you would see that the most influential feature is marital status, which is also kind of obvious if you look at the tree, because the right size, which concludes all the people who are married, has almost only positive predictions, and the left side, that contains only unmarried people, has almost only negative predictions. So marital status is very influential. It's a root node. And the other important interaction is between capital gain and marital status. And if you study the tree long enough, you realize that not like having both capital gain and a good marital status is the way to success in our tree. So there's a good interaction between them. Another interaction methods that's called quantitative input influence gives you a different version. It tells you different things about the influence. For that metric, the interaction between education level and marital status is actually the most important feature. However, quantitative input influence doesn't satisfy monotonicity. And why this is bad, you can see once we change the tree. So now we make a small change to our tree that actually strengthens the interaction between capital gain and marital status. And to do that, we reduce the leaf, the second to last leaf. So now the second to last leaf is a negative prediction. And now it's more important to be both married and have capital gain. So we strengthen the interaction between these two features. And the bands of interaction index noticed and now puts more effort and more interaction on the interaction between capital gain and marital status. However, quantitative input influence is not monotonic, and it just puts more influence on capital gain. Okay, and now we come to the end of this talk. I want to discuss some future work and some other open questions. First, it's important to be able to identify important interactions before we do the computations. You might have noticed that there are 2/n potential sets for which we could calculate the interactions, and that's of course way too many. So it would be good to study how we can figure out for which sets we actually are interested in the interaction, so we can also consider larger sets beyond the size 2. Another thing is past work mainly focuses on the Shapley values, but there are many other solution concepts out there. So we introduced you to the bands of interaction index, but cooperative game theory has decades of history and many proposed methods that might be interesting to study. So we want to say that the game theory fair division community should be an active part of the discussion in algorithmic transparency. And please, of course, check out our full paper for more discussions, where we also demonstrate the importance of the other axioms on more real-life data sets in more depth. And with this, I thank you for your attention.